Let's look at some simple equilibrium reactions and get familiar with the equilibrium expression. Let's say I have the reaction between hydrogen gas and iodine gas. Remember that they're both diatomic, and the product of this reaction is hydrogen iodide gas. Again, to balance it, I'd need the two as indicated here. Again, hydrogen and iodine are diatomic, and so I have to remember that when I write this reaction. The equilibrium expression for this reaction in terms of the concentrations is equal to the products raised to their coefficients divided by the reactants. So I would have this expression. You'll notice that I squared the HI concentration, which is on top, because that is the product and the coefficient is 2. The concentrations of H2 and I2 are both multiplied in the denominator. So this is my expression for my equilibrium constant in terms of concentration, and that's why I have the little c subscript. I also could write the expression for the equilibrium constant in terms of pressures. Which one I use just depends on what data was given. Alright, suppose that a student ran this reaction in the laboratory and collected information on the concentrations of each of these species at equilibrium. And let's say the student discovered that at equilibrium, alright, at some temperature, it is totally possible that these concentrations would be at equilibrium. So if these are the concentrations at equilibrium, what is the equilibrium constant at this temperature? We simply plug in the values and punch the numbers into our calculator. So here we go. We want two significant figures in our answer because of the data, and an equilibrium constant is unitless. Now you might say, well, in this case it is, because all of my molarities cancel. It's not always going to be apparent that the molarities cancel, but if you go on and take physical chemistry, you'll learn the trick to getting the molarities to cancel. For us at the general chemistry level, we're just going to remember that the equilibrium constant is indeed unitless, so just don't worry about units. It's not often you hear a chemistry instructor say that, but don't worry about the units here. So my equilibrium constant is 4.6. The magnitude of the equilibrium constant, if we calculate it or are given it, give us some information about the position of the equilibrium for the reaction. Since the equilibrium constant is a ratio, always a ratio of products over reactants, it's not exactly products or reactants because I have some stoichiometric coefficients in there and I'm multiplying them all together, but you get the idea. If my equilibrium constant is greater than 1, that means this ratio gives me a numerical value that's greater than 1, which means my products are in higher concentration than my reactants in general. So an equilibrium constant that is greater than 1 is often referred to as a product-favored equilibrium. The position of the equilibrium is product-favored. Or I can talk about the equilibrium lies to the right, since there are more products. If, on the other hand, I have that the equilibrium constant is less than 1, that means my ratio would give me a smaller numerical value than 1. My reactants would be on average larger than my products at equilibrium. Reactants are larger than products, and this would be considered a reactant-favored reaction. I also could talk about the fact that the equilibrium lies to the left, or that this is a reactant-favored reaction, or the reaction lies to the left, or this is I'm saying the same thing over and over again. So if equilibrium constant is less than 1, the reactants would be larger than the products at equilibrium, which means this is a reactant-favored reaction.